In this topic, you have learned magnetic field is the space or region around a magnet in which a force is experienced by a magnetic pole. A magnetic line of force is the line joining any two points in a magnetic field. The number of magnetic lines of force present in a unit area is proportional to the intensity of magnetic field in that area.
The magnetic field produced by a current-carrying conductor at a given point depends directly on the current passing through it. If there is a circular coil having n turns, the field produced is n times as large as produced by a single turn.
Now look at the visual. Do you see some lines going between the poles of the magnet? Do you know what these lines denote? These lines denote a specific space or region. Let's see what this is. The space or region around a magnet in which a force is experienced by a magnetic pole is called magnetic field. Let us perform another activity to see the behavior of iron fillings in a magnetic field. Take a cardboard. Place a bar magnet at its center. Sprinkle some iron fillings on the cardboard and tap the board gently. What do you observe? We observe that all the iron fillings get aligned themselves in the direction of the magnetic field. The pattern in which these iron fillings form a line is the direction of line of force in that area. To map the magnetic lines of force, fix a sheet of paper to a drawing board. Keep a bar magnet on the sheet of paper at its center. Now, adjust the drawing board and the north pole of the bar magnet along the geographic north using a compass. Place a plotting compass near the bar magnet. With a pencil, mark the direction of the north pole of the plotting compass. Move the plotting compass in such a way that the south pole of the plotting compass is in alignment with the first point and again mark the second point. Join the first and the second point and mark the direction of deflection. By repeating this action, many more points may be obtained, and the line joining all these points is called the magnetic line of force. Hans Christian Ørsted investigated the relation between electricity and magnetism. After many years of hard work, he experimentally proved the existence of magnetic field near a current-carrying conductor. In his experiment, he showed that when a current-carrying wire was kept parallel to the axis of magnetic needle, the needle was found deflected from its normal position. When current was reversed through the wire, the needle was found to deflect in the opposite direction. Look into this animation to understand Ørsted experiment.
We have learnt about Ørsted's experiment. Let us learn that current-carrying wire behaves like a magnet. Pass an insulated wire through a cardboard hole and connect it to a battery through a key. Sprinkle iron fillings on the cardboard randomly. Close the key and gently tap the cardboard. What do you observe now? Yes, iron fillings arrange themselves into concentric circles. These concentric circular paths indicate the lines of force of magnetic field around the current-carrying wire. Hence, a current-carrying wire has magnetic field.
Let us discuss the magnetic field about current-carrying circular loop. Take a cardboard. Make two holes in it such that the wire passes through it to form a circular loop. Now, the circular wire is perpendicular to the cardboard. Connect the ends of the wire to the battery. Then, sprinkle iron fillings uniformly on the cardboard and gently tap the cardboard. You will observe that the iron fillings form circular loops. From the experiment, you conclude that the magnetic lines of force at the center of the current-carrying loop are almost straight lines. Near the wire are circular and form concentric circles. If the number of turns of the current carrying wire is increased, the magnetic field also increases.
In this topic, you have learned when a current carrying conductor is placed in a magnetic field, it experiences mechanical force. Stretch first 3 fingers of left hand mutually perpendicular to each other. If the forefinger denotes the direction of magnetic field and the middle finger denotes the direction of current, then the thumb represents the direction of mechanical force. This is Fleming's left-hand rule. Electric motor works on the principle of current carrying conductor placed in a magnetic field experiences mechanical force. Electric motor is a device which converts electrical energy to mechanical energy.
We have learned that current carrying conductor behaves like a magnet on passing current. Now, let us discuss the effect of external magnetic field on the current carrying conductor. What happens when current carrying conductor is placed in an external magnetic field? Yes, they experience a force. This force deflects the conductor or moves away from the magnetic field. This mechanical force experienced by a conductor placed in a magnetic field depends on the strength of the current I, length L of the conductor, and the magnetic induction B of the external magnetic field. Therefore, force F is equal to BIL. Now a question arises. What will be the direction of the mechanical force? The direction of mechanical force can be found from Fleming's left-hand rule. Stretch the first 3 fingers of your left hand such that the forefinger, middle finger, and the thumb are mutually perpendicular to each other as per visual. If the forefinger shows the direction of the magnetic field and the middle finger points the direction of flow of current, then the thumb points the direction of the mechanical force. By applying Fleming's left-hand rule, one can find the direction of mechanical force. This rule is also called as motor rule. Click the animation button to know more.
Electric motor is a device that converts electrical energy into mechanical energy. Let us now discuss the construction of DC motor. The main part of a DC motor is the rectangular coil of insulated copper wire wound on a soft iron core. This arrangement is called the armature. It has permanent horseshoe magnet, 2 metallic half rings called split rings forming the commutator, and 2 carbon brushes. These parts are fixed as shown in the visual. The battery, key, brushes, commutator, and the coil form an electric circuit. Now we will see the working of DC motor. Consider the armature coil is in horizontal position. That is, the plane of the coil is parallel to the magnetic field. If the current flows in direction A to B and C to D, AB experiences downward force and CD experiences upward force. This constitutes a couple and so rotates the coil in anti-clockwise direction. Due to the rotation, the coil is turned through 180 degrees, and the arms AB and CD have interchanged the positions. Commutator has changed the current direction. Now CD will be in the position of AB. Thus, CD experiences downward force and AB experiences upward force. Similar action will take place and further rotation continues if the current is supplied continuously.
In the case of commercial motors, we make use of electromagnets instead of permanent magnets. Large number of turns of conducting wires in the current carrying coil and a soft iron core on which the coil is wound. The rectangular coil of insulated copper wire wound on a soft iron core is called the armature. These factors increase the power of the motor.
In this topic, you have learned The phenomenon of producing induced current in coil by changing the magnetic flux in the coil is called electromagnetic induction. Fleming's right-hand rule states that when the thumb, the forefinger and middle finger of the right hand are stretched mutually perpendicular to each other, such that forefinger along the direction of magnetic field and the thumb is along the direction of motion of the conductor, then the middle finger points to the direction of induced current. A dynamo is an electrical device which converts mechanical energy into electrical energy by electromagnetic induction. In 1831, Michael Faraday investigated the relation between electricity and magnetism by conducting a number of simple experiments that led to the invention of electromagnetic induction. The production of electromotive force in a coil due to changing magnetic flux linked with the coil is called electromagnetic induction. Now, let us learn Faraday's experiment to understand electromagnetic induction. Take a copper coil and galvanometer. Connect them with connecting wires. Now, take a bar magnet. Move the bar magnet swiftly towards the coil such that the north pole of magnet faces the coil. You can see the deflection in the galvanometer. If you move the magnet away from the coil, the deflection of the galvanometer is in the opposite direction. If you repeat the experiment by changing the face of the pole, the direction of current changes. You can also observe the same kind of deflections in the galvanometer when coil is moved front and back from the fixed magnet. From the observation, we can understand that the relative motion of the coil or the magnet induces current in the circuit. If we keep magnet and the coil stationary, then no current is induced. The current produced by the relative motion of the coil or the magnet is called an induced current, and it is set by an induced electromotive force. This phenomenon of producing induced electromotive force by the relative motion of the coil and magnet is called electromagnetic induction. Now, let us discuss the direction of flow of induced current. Fleming's right-hand rule is useful to find the direction of induced current in a linear conductor. When the thumb, the forefinger and the middle finger of the right hand are stretched mutually perpendicular to each other and are held such that the forefinger is along the direction of magnetic field and the thumb is along the direction of motion of the linear conductor, then the middle finger points along the direction of the induced current or induced electromotive force. Consider a straight conductor placed in uniform magnetic field. The magnetic field direction is toward left side. If the conductor is moved up, then the induced current flows towards you. Click animation button to know more. Now let us learn about AC generator. AC generator or dynamo is an electrical device which converts mechanical energy into electrical energy, utilizing the phenomenon of electromagnetic induction. AC generator consists of a rectangular armature A, B, C, D between two powerful magnetic poles N and S. The terminal from AB is connected to slip ring S1 and the terminal from CD is connected to S2. The carbon brushes are in contact with the slip rings. If the loop is rotated in anti-clockwise direction, the AB goes down and CD comes up, and so the current flow from A to B and C to D from S1 to S2 for the first half rotation. Thus, ABCD turns to 180 degrees, then position of ABCD is interchanged. If the rotation is continued, the current flow from D to C and then B to A and S2 to S1, the rapid rotation of the armature in the dynamo generates current or voltage in the external circuit whose direction alternates for every half cycle, so as to produce an alternating current. The working principle of DC generator is same as that of AC generator. The only change in the construction is the slip rings are replaced by split rings. Thus, the split ring changes the direction alternatively and produces an unidirectional current through the circuit.